Assalamualaikum and salam sejahtera. This video will be a discussion on assignment 8, which is a topic on introduction to Laplace Transform. Question 1 asks you to use the initial and final value theorem to find f of 0 and f of infinity for the f of s below. One of the properties of Laplace transform is the initial and final value properties, which allows you to find the initial value f of 0 and the final value f of infinity of the f of t directly from the f of s. So basically, you don't have to transform this f of s into f of t, but you just straight away use this f of s to find the initial and final value. So how you would find the initial value is to apply this equation. So you find f of 0 by finding the limit of s approaches infinity of s times f of s. So from here we notice that the highest power of the denominator and the numerator is s squared. So as s approaches infinity, or s gets bigger and bigger and bigger, the s squared terms will get very large and going to be much more significant than the constants. So the initial value will become 6. To find f of infinity, you just find the limit as s approaches infinity of s times f of s. So basically for this one, you just replace all the s with 0 and you will find that f of infinity is equals to 0. Okay, question 2 asks you to find the f of t given the following f of s. So for any question that asks you to find f of t, you need to use this Laplace transform table, which is available in your book. If I'm not mistaken, it's a table 15.2 in your book. And you need to try to decompose your f of s to actually match the f of s given in this Laplace transform table. Okay, first what we can do is we decompose the f of s. We know that f of s have 3 poles, so there will be 3 parts of this decomposed f of s. So f of s is decomposed into a over s plus 1 plus b over s plus 2 plus c over s plus 3. So next we have to solve this a, b and c term. So there's multiple methods that you can use. First is the residue method, and there's also an algebraic method, and there's also a method where you can combine the two. So specifically for this question, I will use the residue method to solve for the A, B, and C. So basically for the residue method, what you have to do is you have to eliminate the respective term associated with the poles in the f of s and replace the s with the poles. What I mean is, for example, to find A, you eliminate the s plus 1 term by multiplying f of s with s plus 1. Then you replace all the s's, all the remaining s's with the pole, which is minus 1. So you will find A to be negative 5. Similarly, you will find B by eliminating the s plus 2 term and replace all the remaining s's with the minus 2, and you will find B to be 20. Use the same technique to find C, which is going to be minus 15. So we rewrite everything once we have solved for the coefficients, and we try to find the inverse of each term by matching the form with the one available in the table. So rewriting everything, we have this form, and if we go back to the Laplace transform table, we can see that the form that is most similar to the one we have is the 1 over s plus a, and this will transform the f of s into e to the minus at. So the overall f of t is given here. Okay, question 3 also asks you to find f of t for the given f of s in this slide. Okay, the steps that you have to follow is similar, but because you have the s squared term here, there will be a further manipulation of the decomposed term that you have to do to match the term with the term in the Laplace transform table. Okay, let's do this. First, we decompose f of s into two parts. Specifically for this question, I combine both the algebraic as well as the residue method. So in finding A, I use the residue method because it's easier that way. Okay, so we eliminate s plus 2 by multiplying the f of s with s plus 2 and replace all the remaining s's with minus 2, and I obtain A to be minus 1. Okay, to find B and C, I use the algebraic method. So I multiply both sides of this highlighted equation with s plus 2 and s squared plus 2s plus 5, and I will end up with this equation. Then you have to equate the coefficients of the right hand side with the left hand side. Okay, first we look at the s squared terms first. So on the left hand side, there is no s squared terms. Okay, but on the right side, there are s squared terms, which is a plus b. So we have to equate this together. Okay, so by just looking at the s squared term, we know that the a plus b equals to 0. We already solved for a, which is minus 1. So we know that b equals to negative a, which is equals to 1. Okay, next we equate the coefficient of the s to the power of 1, or just s. Okay, so on the left hand side, we see that the coefficient is 3s. And on the right hand side, we have 2a plus 2b plus c. Okay, so just by looking at the s, we know that this 2a plus 2b plus c equals to 3, and we already have a and b, and we substitute that into this equation, and we find that c equals to 3. Okay, so now that we know a, b, c, we rewrite everything back, and again, we have to try to match this equation to the form that is available in the Laplace transform table. So we already know this part here, right? It's similar to the one in equation 2. So now we have to deal with the part that have the denominator s squared plus 2s plus 5. This one. Alright, let's deal with this part. We have the Laplace transform table here. And we can see that the term that is almost similar to the form that we have now is these two here, the one with the sine omega t and cosine omega t. However, we notice that the denominator is not in the correct form. So we have to somehow manipulate the denominator to match this form in the table here. The s squared plus 2s plus 5 is actually can be written as s plus 1 squared plus 2s. Okay, now we can see that the denominator have the same form as the one in the table. However, the numerator is still not the same. Okay, we can see that the a have to match and the omega also have to match. So we have to decompose the equation that we have to further decompose it to match the form in the table. After decomposing, we find that we can actually rewrite the f of s just like what is shown in the slide, and now we can see that the a matches and also the omega matches, so we can use these two here to transform our f of s into f of t. So the overall f of t for this f of s is shown in this slide here. So just to recap, you have to manipulate the equation that you have to match the one in the Laplace transform table if you want to find the f of t. Okay? Okay, last question. You basically need to identify the output y of t given the transfer function h of s and the input u of t. Okay, now you have to dissect the problem. You can see that your output you want is y of t. Your input is also in your time domain, which is u of t. But your transfer function is in the s domain h of s. So firstly, you have to convert your input into the S domain. So just use the table. We can see that the u of t can be transformed into the S domain and it will become 1 over S. Okay, now your transfer function in S domain and your input in S domain. So what is your output in the S domain? H of S, which is the transfer function, is always equals to the output over the input. So output is just your H of S times your X of S. So we already know just now your X of S is 1 over S. So we just multiply the two together. From this point forward, you can just use any method that was already discussed in the previous question. You can use algebraic, you can use residue method. I personally like the residue method. So I found that A to be 6 and B to be minus 6. And then you rewrite the equation, plug in the A and the B and use the Laplace transform table to find the y of t. Okay, so that's it for this week. So as usual, I will give 2 to 3 questions, very easy question. If you go through this video, you will find the answer within the videos. And you have to answer it and pass it back to me via Microsoft Teams just to show your participation in this week's tutorial. Alright, thank you very much.